Welcome to the other physics lecture video. Now today we will discuss all about magnetic field and magnetic forces. Everybody uses magnetic forces. They are at the heart of electric motors, microwave ovens, loudspeakers, computer printers, and desk drives. The most familiar examples of magnetisms are permanent magnets. The fundamental nature of magnetism is the interaction of moving electric charges. Unlike electric forces, which act on electric charges whether they are moving or not, magnetic forces act only on moving charges. Magnetism. Magnetic phenomena were first observed at least 2,500 years ago in fragments of the magnetized iron ore found near the ancient city of Magnesia, now Manisa in western Turkey. These fragments were examples of what are now called permanent magnets. Permanent magnets were found to exert forces on each other as well as on pieces of iron and were not magnetized. Before the relationship of magnetic interactions to moving charges was understood, the interactions of permanent magnets and compass needles were described in terms of magnetic poles. If a bar-shaped permanent magnet or bar magnet, for conveniency, is free to rotate, one end points north. This end is called North Pole or N pole. The other end is a South Pole or S pole. Opposite poles attract each other, and like poles repel each other. An object that contains iron but is not itself magnetized, that is, it shows no tendency to point north or south, is attracted by either pole or the permanent magnet. This is the attraction that acts between the magnet and the unmagnetized steel door of a refrigerator. By analogy to electric interactions, the bar magnets set up a magnetic field in the space around it, and the second body responds to that field. A compass needle tends to align with the magnetic field at the needle's position. The Earth itself is a magnet. Its north geographic pole is close to a magnetic south pole, which is why the north pole of a compass needle points north. The Earth's magnetic axis is not quite parallel to its geographic axis. So, a compass reading deviates somewhat from geographic north. This is a sketch of the Earth's magnetic field. The field, which is caused by currents in the Earth's molten core, changes with time. Geologic evidence shows that it reverses directions entirely at irregular intervals of 10 to the power of 4 to 10 to the power of 6. Now, the north geographic pole, Earth's rotation's axis. The geomagnetic North Pole is actually a magnetic South Pole. It attracts the N pole of a compass. Magnetic field lines shows the direction of the compass. The concepts of magnetic poles may appear similar to that of electric charge, and the north and the south poles may seem analogous to positive and negative charge. But the analogy can be misleading. While isolated positive and negative charge exists, now there is no experimental evidence that a single isolated magnetic pole exists. Poles always appear in pairs. Now, if we have a bar magnets, which we would break it into two, each broken end becomes a pole. We have two existing magnets. Each has a north and a south poles. Taking time for the history, the first evidence of the relationship of the magnetism to moving charges was discovered in 1820 by the Danish scientist Hans Christian Ørsted. He found that a compass needle was deflected by a current-carrying wire. Similar investigations were carried out in France by André Ampère, a A few years later, Michael Faraday in England and Joseph Henry in the United States discovered that moving a magnet near a conducting loop can cause a current in the loop. Now, in Orsted's experiment, a compass is placed directly over a horizontal wire. When the compass is placed directly under the wire, the compass deflections is reversed. Magnetic field. Now, the concept of magnetic field is greatly similar to that of electric interactions. Now, we can describe magnetic interactions. First, a moving charge or a current creates a magnetic field in the surrounding space. Second, the magnetic field exerts a force F on any other moving charge or current that is present in the field. Now we'll more focus on the second description of the magnetic field, which states that the magnetic field exerts a force on any other moving charge or current that is present in the field. Like electric field, magnetic field is a vector field, that is, a vector quantity associated with each point in space. We'll use the symbol B for magnetic field at any position of the direction of B is defined as the direction in which the north pole of a compass needle tends to point. Magnetic forces on moving charges. There are four key characteristics of the magnetic force in a moving charge. So first, we have the magnitude is proportional to the magnitude of the charge. So here, F or subscript M is denoted is equivalent to the magnitude of the magnetic force. So the first characteristic is that magnetic force is proportional to the charge of the particle. So for example, if we have a 1 microcoulomb and 2 microcoulomb charges, with having a constant velocity or the constant velocity, so the magnetic force Fm, so here, of the 2 microcoulomb is twice as great as the magnetic force of 1 microcoulomb. So that is the first characteristic. Now, the second characteristic of the magnetic force in a moving charge is that magnetic force is also proportional to the strength of the magnetic field. So if we have, for example, two identical magnets having the velocity and the charge of that particle is constant, so the one magnetic field is equivalent to one magnetic force, where the two magnetic field is equivalent to 2 magnetic force, or the 2 magnetic field, the magnitude of the magnetic field is 2. The magnetic force of the 2 magnetic field is twice as great as the magnetic force of the 1 magnetic field. So that is the second characteristic. Now, the third characteristic of the magnetic force in moving charges is that the magnetic force depends on the particle's velocity. Now, if we have a rest particle, then the magnetic force in that particle is 0, since the magnetic force is always governed in the moving charges. So if our particle is at rest, then the magnetic force is 0. Now we have the fourth characteristic of the magnetic forces. So it states that the direction of the magnetic force is always perpendicular to the magnetic field and the velocity v of the particle. So to sum up the the four characteristics of the magnetic force. So we have the magnetic force M, or the magnitude of the magnetic force, is equal to the, since it is proportional to the charge Q and depend on the velocity V, times the proportional to the magnetic field B. So that is the magnitude of magnetic force. So magnetic force is equal to Q V B sine phi, where phi here is the angle between the velocity of the particle and the magnetic field B. So in general, the magnetic force is equal to Q V cross B. So in determining the direction of the magnetic force, we use right-hand rule. So we should review the right-hand rule formula, or the right-hand rule. So for example, if we have a velocity v moving at the direction of the x-axis, so this is v moving at the x-axis, positive x-axis rather. So, and we have if we have a magnetic field along with the y-axis, so this is the direction of our magnetic field. So this is the magnetic field. So our magnetic force, direction of our magnetic force is that, using right-hand rule, to the direct your four fingers to the direction of your velocity, and curve your palm to the direction of your magnetic field. So here. Then the direction of where your thumb point is, that is the direction of your magnetic force. So here in our example, the direction of our magnetic force is into or out of the page or into the camera, right? So we denote that as the z-axis. So the direction of our directed to the positive z-axis. So that is the direction of our magnetic force. So the units used in magnetic force is that 1 Newton per ampere that meter, or it is commonly used units for magnetic force is Tesla. So that is 1 Newton per ampere that meter is equal to 1 Tesla. Or another unit for magnetic force is the Gauss. So 1 Gauss is equal to 10 to the 4th Tesla. So that are the units of magnetic forces. So when a charged particle moves through a region of space where both electric and magnetic fields are present, both fields exert forces on the particle. So the total force is the vector sum of the electric and the magnetic force. So electric force is equal to Q E and R. So that is Fe to denote force in the electric field. So the magnetic force is, we have Q V B. So the total force when a charged particle moves in a space region where both electric field and magnetic field are present is equal to the total sum of this electric force and magnetic force. So we have Q E plus Q V B, or simply to put, Q E, a Q times E plus V. V B is cross B. So that is the total force of the particle, charged particle moving in a space region where both electric field and magnetic field are present. Let's have some examples. Here, a beam of protons at 3.0 times 10 to the 5 meter per second through a uniform 2.0 Tesla magnetic field directed along the positive z-axis, the velocity of each proton lies in the xz plane and is directed at 30 degrees to the z-axis. Find the force on a proton. So here, we have given the velocity of the proton, which is equal to 3 times 10 to the power of 5 meter per second. So that is the velocity of the proton. And another given is that we have the magnetic field, 2 Tesla. So that is the magnetic field. That is the magnetic field. And it is directed along the z-axis. So the velocity of each proton lies in the xz plane. So to execute the problem, we have solution. So we use the relationship of the magnetic force is equal to Q V B sine phi for the magnitude of our magnetic force. So this is the magnitude of our magnetic force. So we have given the charge of the proton is 1.6 times 10 to the negative 19 coulomb times the velocity of the proton, which is 3.0 times 10 to the power of 5 meter per second, times the magnetic field, which is 2 Tesla, and the phi, which is 30 degrees, so we have sine 30 degrees. So, through calculation, we have 4.8 times 10 to the negative 14 Newton is the magnitude of the magnetic force. Now, what is the direction of the magnetic force? So, if we have here, using the vector language, we have given the velocity 3 times 10 to the 5 meter per second at the xz plane. So we have sine 30 degrees I hat plus cosine 30 degrees k hat, since it is xz. So j hat is 0 since it is only at xz plane, where our magnetic field is 2.0 Tesla at the z-axis. So it is k hat. So using the product rule, so F QV times B. So, inputting all values here. So, input all values 1.6 times 10 to the negative 19 coulomb times 10 to the negative 5 meter per second times 2 Tesla cross sine 30 degrees I hat plus cosine 30 degrees k hat cross k hat. So, we have negative 4.8 times 10 to the negative 14 Newton J hat. So this is the magnitude of our magnetic force. And the direction of our magnetic force is along the negative J hat. So if we use not proton but electron, so we have negative 1.6 times 10 to the negative 19 coulomb. So the direction of our magnetic force, the magnitude of our magnetic force is the same since they have the same magnitude of charge, but the direction is opposite to the one to proton. So since the proton is directed to the negative j hat, so the direction of the electron is along the positive j hat. So that is how the charge or the charge of the particle affects the direction of the magnetic force. Since magnetic field is in three-dimensional, it's often necessary to draw magnetic field lines that point into or out of the plane of the drawing. So, to represent this, we use dot to represent out of the page. The direction of the magnetic field is out of the page, and cross as into the page. So, if dot, meaning to say that the direction of your magnetic field is out of the page. So, since if this is our page, the paper here, this is our page, so the magnetic field, if that is the symbol, so mean to say, the direction of your magnetic field is going to the camera, like that. While if cross is used, then from the camera to the page. So that is the direction of your magnetic field. So we have the magnetic flux and Gauss law for magnetism. So we define magnetic flux, or the symbol here is the magnetic flux, through a surface, just as we described the electric flux in connection with the Gauss law. So we can divide any surface into elements of area dA. So for each element, we determined B perpendicular. So the B perpendicular is the component of B normal to the surface at the position of that element. So from the figure, so here is the figure. So this is the area A. So we take some element dA, small infinitesimal area dA here. So the direction of our magnetic field is going to is denoted by the red mark here. That is the direction of our magnetic field. Since the B perpendicular, or the magnetic field perpendicular to the surface, and we have the B parallel to the surface. So the B perpendicular to the surface is equal to B cosine theta, cosine phi. So phi here is the direction from the perpendicular magnetic field, the component of the magnetic field perpendicular to the surface, and the direction of the magnetic field. So here, so the area, so dA is the area, or the infinitesimal area, or the small element of the area, where the B perpendicular is the component of magnetic field normal to the surface. So B perpendicular is equal to B cosine phi. So our magnetic flux is equal to the B perpendicular times the area, or B cosine phi dA, or it is equal to the magnetic field dot dA. So therefore, our magnetic flux is equal to the integral of B perpendicular dA, or B cosine phi dA, or equal to B dot dA. So that is the magnetic flux. So the magnetic flux is a scalar quantity. So if B is uniform, if B is uniform, so we have the magnetic flux is equal to BA, or B cosine A, and the unit for magnetic flux is Weber. So 1 Weber is equal to 1 Tesla dot meter squared. So the total magnetic flux through a closed surface is always 0. So this is the Gauss law for magnetism. So in every closed surface, the total magnetic flux through a closed surface is always 0. So in Gauss law, the total electric flux through a closed surface is proportional to the total electric charge enclosed by the surface. So by analogy, if there were such thing as a single magnetic charge or magnetic monopole, the total magnetic flux through a closed surface would be proportional to the total magnetic charge enclosed. But we have mentioned that no magnetic monopole has ever been observed. So there must exist two unlike charges, the north and the south pole, to exist to have a magnetic field. So despite intensive research, so we conclude that the total magnetic flux through a closed surface is always 0 since mag-cancel out ang mga charges. So this equation is sometimes called the Gauss law for magnetism. So this is magnetic flux through any closed surface. No, if the element of the area dA is at the right angle to the field lines, then B perpendicular is equal to the B. So calling the area dA perpendicular. So we have now the B is equal to the magnetic flux over the area. So this is the flux per unit area, or it is sometimes called the magnetic flux density. So this is the equation for magnetic flux density. So let's have some examples. A plane of 3.0 centimeter squared is inclined with 30 degrees in a uniform magnetic field. The magnetic flux is positive 0.9 milliweber. Find the magnitude of the magnetic field and the direction of the area vector A. So here, we are given with an area of equal to 3 times 10 to the negative 4 meter squared. So I converted already the centimeter squared to meter squared. So this is the conversion. Since we can directly conclude that since it is a uniform magnetic field, the direction of our area vector area A is perpendicular to the surface. Perpendicular to the surface. So here, so this is our drawing. So this is the direction of our magnetic field B, and this is the 30 degrees inclination of our plane to the magnetic field. So therefore, the B perpendicular to the surface. So this is so I use red color to emphasize. Okay, this is the B perpendicular to the surface. So we have two options here, right? From the B perpendicular to B, so we have two options here. It's because we could actually use this angle or this angle. But take note that our magnetic field and our magnetic flux is positive, so we use the one that we could get the positive, or this angle here. So that is equal to 60 degrees. So that is equal to 60 degrees. So therefore, from our equation of the magnetic flux, which is equal to BA cosine phi, so our magnetic field here is equal to our magnetic flux all over A cosine phi. So input all values, we have 0.9 milliweber. Milliweber is equal to times 10 to the negative 3 Weber all over 3 times 10 to the negative 4 meter squared times cosine 60 degrees. So through calculations, we could get the magnitude of the magnetic field with 6.0 Tesla. So this is our magnetic field. When a charged particle moves in a magnetic field, it is acted on by a magnetic force, and the motion is determined by Newton's laws. So, for example, if we have a particle here, a positive particle, moving at the velocity v at this direction, and our magnetic field is directed x, meaning to say that is directed into the page. So here is the direction of our magnetic field. That is the direction of our magnetic field. So the direction of our magnetic force is perpendicular to the direction of our magnetic field and velocity. So this is the direction of our magnetic force. So the magnitude of our magnetic force is equal to magnetic force is Q V times magnetic field. So this is the magnitude of our magnetic force. So the force is always perpendicular to V. So the force is always perpendicular to V, so it cannot change the magnitude of the velocity, only its direction. So to put it differently, the magnetic force never has a component parallel to the particle's motion. So the magnetic force can never do work on the particle. So this is true even if the magnetic field is not uniform. So therefore, the motion of a change of the charged particle under the action of the magnetic field alone is always motion of the constant speed. So using this principle, we see that the situation here, the magnitudes of both F and V are constant, right? So at points such as this is, for example, this is point O. At point here, the velocity is directed here, while the magnitude of or the direction of our magnetic force is always perpendicular to our velocity. So the direction of our force is here. So if we have our points here, the direction of our velocity is directed towards, and the force is perpendicular to the velocity. So this is the F, the V. So we could denote that we could observe that the direction of the particle is in circular motion. So here, this is the motion of our particle. So the directions of the force and velocity have changed as shown here in our example. But their magnitudes are the same. So the particle therefore moves under the influence of the constant magnitude force that is always at the right angles to the velocity of the particles. So comparing this to our circular motion discussion, so we see the particle's path is a circle, tracing out with a constant speed v. So the centripetal acceleration is equal to v squared over r. So this is the centripetal acceleration. So using this Newton's second law, we have F is equal to ma. So our F here is equal to qvb, or mass of the particle times the centripetal acceleration, which is v squared over r. So that is the relationship. So combining, this is the relationship between the magnetic force at the motion of the particles moving with the influence of the magnetic field. So we could actually get the radius of the path of the circular path, the radius of the circular path of the motion of the particle. So r here must be equal to, using algebra, so it is equal to mv over qb, or mv is our momentum. We could actually express this as P over QB. So that is the radius of the circular path, the motion of the particle here. So we can also write R in terms of the momentum here. So the angular speed of the particle can be found as the angular speed is equal v is equal to the radius times the angular speed. So we could actually denote angular speed as a v over r, or equal to v times qb over mv. So we could cancel the v. We have qb over m. So this is the angular speed of the particle. So the number of revolutions per unit time is equal to F is equal to the angular speed over 2 pi. So this frequency is independent rather. So this frequency is independent of the radius of the path. So it is called the cyclotron frequency. So this is the cyclotron frequency. So you could actually, F is equal to our W. We have QB over M times 1 over 2 pi. So this is the cyclotron frequency. So in a particle accelerator called a cyclotron, particles moving in nearly circular paths are given a boost twice each revolution, increasing their energy and their orbital radii, but not their angular speed or frequency. Similarly, one type of magnetron this is a common source of microwave radiation for microwave ovens and radar systems, emits radiation with a frequency equal to the frequency of the circular motion of the electrons in a vacuum chamber between the poles of a magnet. So, if the direction of the initial velocity is not perpendicular to the field of the velocity component, so parallel to the field is constant because there is no force parallel to the field. So if we have the x here, this is the y-axis, this is the x-axis and the z-axis. So if the initial velocity is not perpendicular to the field, so the velocity of the component parallel to this field is constant, right? So constant ang iyang v parallel. So means say ang iyang v perpendicular, if this is the initial v, so our v perpendicular here, this is the v perpendicular. If our initial velocity is not perpendicular to the direction of our magnetic field, then the v perpendicular, then the shape of the path of the particle is helical or in helix. So that is the path of the particle in helix form. So for example, a magnetron in a microwave oven emits electromagnetic waves with a frequency of 2450 megahertz. What magnetic field strength is required for electron to move in a circular paths with this frequency? So to execute this, we have given the angular speed that corresponds to the frequency. So the angular speed that corresponds to the frequency is equal to 2 pi f. So our angular speed is equal to 2 pi times our frequency, which is 2450 megahertz, so to the 10 to the power of 6 hertz, which is equal to, through calculation, we have 1.54 times 10 to the power of 10 second inverse. So from our equation for the angular speed, which is equal to QB over M, so our B here, we could actually get our B as angular speed times mass over Q. So, inputting all the given values, we have the angular speed, which is 1.54 times 10 to the power of 10 second inverse, times the mass of our electron, which is equal to 9.11 times 10 to the negative 31 kilogram. So this is the mass of the electron. All over, the charge of the electron is the absolute value. We have the absolute value. We have 1.6 times 10 to the negative 19 coulomb. And our V here is equal to 0.0877 Tesla. So this is the magnitude of our magnetic field. To execute this, we have the magnetic force is equal to F is equal to QV times B. So Newton's second law gives the resulting acceleration. Because F is perpendicular to V, so the proton's speed does not change. So the radius of the helical trajectory, if we replace V with the velocity component perpendicular to B, so it will gives the angular speed, which yields the time t for one revolution, or the period given the velocity component parallel to the magnetic field. So we can then determine the pitch. So here A, we have given the magnetic field, which is equal to, along with the x-axis, and our V, the direction of our V here, our vector V is, we have Vx I hat plus Vz k hat. So it will yield us from the equation F is equal to QV times B. This is equal to Q times Vx I hat plus Vz k hat times B I hat, which may result to QVZ J hat. So this is the along in the J hat, positive J hat direction is the R magnetic force. So inputting all values, we have 1.6 times 10 to the negative 19 coulomb times the velocity, which is 2 times 10 to the 5th meter per second times 0.5 Tesla J hat. So the magnitude and the direction of our magnetic force is equal to 1.6 times 10 to the negative 14 Newton J hat. So from Newton's second law, which is F is equal to ma, so therefore we could get the acceleration as A is equal to F over m, which is equal to 1.6 times 10 to the negative 14 Newton all over 1.67 times 10 to the negative 27 kilogram, which yields to 9.58 times 10 to the 12 meter per second squared. So this is directed to the positive j hat. So that is the acceleration of the particle. So since Vy is equal to 0, then the component of the velocity perpendicular to B is Vc. So V perpendicular, which is equal to Vz perpendicular to B. So we could actually get the radius of the particle, or the path of the particle, which mvz all over q, the magnitude of our charge, times b. Inputting all values, we have 1.67 times 10 to the negative 27 kilogram times the velocity of the v at the z direction. We have 2 times 10 to the 5th meter per second all over 1.6 times 10 to the negative 19 coulomb times 0.5 Tesla. So the radius of the path of the particle is 4.18 times 10 to the negative 3 meter, or equal to 4.18 millimeter. So this is the radius of the particle. So the angular speed is equal to qb all over the mass of the particle. So inputting all values, we have 1.6 times 10 to the negative 19 coulomb times the magnetic field, which is 0.5 Tesla, all over 1.67 times 10 to the negative 27 kilogram. So our magnetic angular speed, the angular speed is equal to 4.79 times 10 to the 7 rad per second. So the period is equal to t is equal to 1 over f. So our f is equal to angular speed over 2 pi. So we could get that the period is equal to 2 pi all over angular speed. So inputting values, 2 pi over 4.79 times 10 to the negative 7 rad per second. So we have the period is equal to 1.31 times 10 to the negative 7 second. So now, the pitch is the distance traveled along the x-axis in this time. So therefore, we get earlier that Vx and use the time or the period t. So distance is equal to Vx times time, so which is equal to 1.5 times 10 to the 5 meter per second times the time, what is 1.31 times 10 to the negative 7 seconds. So we could get that the pitch or the distance traveled along the x-axis in this time is equal to 0.0197 meter or 19.7 millimeter.
magnetic force and a current carrying conductor. Now, what makes an electric motor works? Now, within a motor are conductors that carry currents, as well as magnets that exerts forces in the moving charge. Hence, there is a magnetic force along the length of each current-carrying conductor, and these forces make the motor turn. Now, we can compute the force in the current-carrying conductor starting with the magnitude of the force of the magnetic force, which is equal F, which is equal to Q V cross B, single moving charge. Now, if we have a current carrying conductor with a some length L, okay, with some length L, and it is placed in a uniform magnetic field perpendicular to the plane of this conductor and directed into the plane. So the magnetic field is directed into the plane of the part conductor. So here. So that this is the magnetic field. So this is the magnetic field. Now, let's assume first that the moving charges are positive. So the drift velocity, so positive charge. So the drift velocity is upward, perpendicular to the magnetic field. So this is the drift velocity. So the average force on each charge is this F is equal to QV times B, or cross B. So the magnitude of this force is equal to the magnitude of this force, which is equal to QV B. Since the V and B are perpendicular. So we can derive an expression for a total force on all the moving charges in this length L of conductor with the cross-sectional area of A. Okay? This conductor have a cross-sectional area A. So the number of charges per unit volume is N. So the number of charges is N. So the segment of conductor with length L has volume equal to AL and contains the number of charges equal to NAL. This is the number of charges in this volume. So the total force on all the moving charges in this segment has magnitude equal to F is equal to NAL, or the number of charges in this volume times Q, the drift velocity, and the magnetic field. So, by this, we could also define some important quantity here. The current density, which is denoted by J. So the current density is equal to the current over or per unit area, which is equal to NQVD. So this is the general expression for the current density. The value of the current is equal to NQVD times A. So for the total force, which is equal to NAL QVD B, we could simply put that NL and QVD is equal to the current. So the total force of this current carrying conductor is equal to I, or the current, times the length of the conductor times the magnetic field. So if the field is not perpendicular to the wire but makes an angle with it, so we handle the same situation we did earlier for a single charge. So only the component will be perpendicular to the wire. So therefore, our F, if with some angle phi, so I L B sine phi. So the magnetic force on the wire segment is given by this. This is the magnitude of the magnetic force in the wire segment. So the force is always perpendicular to both. The force is always perpendicular to both the conductor and the field, with the directed determined by the same right-hand rule we used for moving positive charge. Hence, this force can be expressed as a vector product, just like the force in a single moving charge. So we represent the segment of the wire of a vector L, a long wire with the direction of the current. Then the force F on this segment is equal to the cross product. So F is equal to the current, then the cross product of length times the magnetic field. So this is the magnetic force on the straight wire segment. If the conductor is not straight, so we have a curve, for example, we have a curve like that, curved wire. So the force dF on each segment, we can divide it into infinitesimal segments. So the dF, or the infinitesimal force in each segment, is equal to I dL cross B. So this is the magnetic force on an infinitesimal wire section. So F is equal to the integral of I dL IB dL. So this is the magnetic force of the general expression for the magnetic force of any wire segment. So for example, a straight horizontal copper rod carries a current of 50 ampere from west to east in a region between the poles of a large electromagnet. In this region, there is a horizontal magnetic field toward the northeast that is 45 degrees north of east, with magnitude 1.2 Tesla. A. Find the magnitude of the direction of the force on a 1 meter section of a rod. B. While keeping the rod horizontal, how should it be oriented to maximize the magnitude of the force? What is the force magnitude in this case? So our sketch on the copper rod, the magnetic field. The magnetic field is directed at the northeast. So this is the magnetic field, forming a 45 degrees angle. So the current is along with the moving toward east, which has the magnitude of 50 ampere. So the 1.2 Tesla. So here we must find the magnetic force on this system. So the magnitude of the magnetic force is equal to I times length times the magnetic field sine phi, which is equal to 50 ampere times the length of R is 1 meter. So we have 1 meter times 1.2 Tesla sine 45 degrees. So the magnitude of the force, the magnitude of the magnetic force in this current carrying conductor, straight conductor, is equal to 42.4 Newton. So we could actually, by using the right-hand rule, the direction of this magnetic force is along the positive z-axis or the k hat. You could verify it using right-hand rule. So the direction of the force is perpendicular to the plane of the current and the field, so both of which is a horizontal plane. Thus, the force must be vertical. The right-hand rule shows that it is vertically upward or out of the plane in this figure. So the second question is that how should it be oriented to maximize the magnitude of the force? Now, to maximize the magnitude of the force, we should need phi must be equal to 90. So therefore, if we have this orientation, the north, east, west, and the south, so our rod must be oriented 45 degrees southeast. So therefore, our rod must be like this. So that this is our B, and the direction of R is going to southeast, forming 90 degrees. So, therefore, the maximum force F is equal to ILB sine phi. So, phi is 90, sine 90 is equal to 1. So, therefore, ILB, which is inputting all values, we could get actually the maximum force when the wire is oriented 45 degrees or southeast, 60 Newton. The magnetic field B is uniform and perpendicular to the plane of the figure pointing out of the page. So the conductor carrying current I to the left has 3 segments. First, a straight segment with length L perpendicular to the plane of the figure. Second, a semicircle with a radius R. And third, another straight segment with length L parallel to the x-axis. Find the total magnetic force on this conductor. So, we are now to find the total magnetic force on the conductor, not a straight line, but a curved conductor, involving curved conductor. So, to illustrate, so this is how it looks like. So, our magnetic field is out of the page. So, we have dot. We use dots. And our first segment is that the straight segment with length L perpendicular to the plane of the figure. So, perpendicular to the plane of the figure, we have directed out of the page, into the page. So, this is the first. We have a semicircle with length, with radius R. And parallel to the x-axis. This is our 2 or 3. So since this is our x-axis and our y-axis. Okay. Here. So for segment 1, here, our L is negative LK, since it is directed into the page. Hence, from F is equal to IL cross B. So our L is K hat and our B is K hat. Therefore, the force in this segment is 0. As a review, K hat cross K hat or is equal to 0. So, that is for our segment 1. We should get segment 3 since it is easier to get first. So, in our segment 3, L here, our L here is equal to negative L I hat. Negative since it is directed toward the negative x-axis. It's directed toward the next negative x-axis since the direction of our current is like that. So the direction of our current will determine the direction of our L, vector L. So using F is equal to I L cross B, so we could get that I L I hat, negative L I hat, cross B K hat. We could determine that I L B J hat. So that is in segment 3. Now in our segment 2, we have here the direction of our current is going to the left. This is the direction of our current, and this with some radius r. So for the curved segment DL, so we take some small portion here DL with a length of r d theta. So at angle theta. So the right hand rule shows that the direction of the DL is radially outward from the center. Radially outward from the center means to say that it is directed toward the J hat, toward the positive J hat. So the magnitude of dF2 of the force of the segment DL is just dF2 equal to I dL B, which is equal to our DL is RD theta B. So we have an X and Y components here. So our dF2X is equal to I R d theta B cosine theta. And our dF2Y is IR d theta B sine theta. So to find the components of the total force, we integrate these expressions with respect to theta from 0 to pi to take the whole semicircle. So the result, so our dF2x is equal to IRB integrated from 0 to pi cosine theta d theta. So the integral of cosine theta d theta, cosine theta is equal to sine. So RB negative sine theta integrated from 0 to pi. So 0, sine 0 is 0 and sine pi is 0. So therefore, dF2x is equal to 0. Where our FD2y is equal to IRB integral of 0 to pi from integral of sine theta d theta from 0 to pi. IRB, we have cosine theta from 0 to pi. We have cosine pi minus cosine 0 is equal to, it's again the integral of sine theta d theta is negative cosine theta and positive din siya diri. So negative cosine theta, so IRB times 2. Therefore 2IRB. So this is the dF2y. So the total magnetic force, adding the forces of all three segments, we find that the total force F is equal to F1 plus F2 plus F3, which is equal to 0 plus 2I RB J hat plus I LB J hat. So we obtain, so B IB times 2R plus L J hat. So this is the total force or the net force of the problem. force and torque in a current loop. A current carrying conductors usually form a closed loop. As an example, let's look at a rectangular current loop in a uniform magnetic field. So we can represent the loop as a series of straight line segments. So we will find that the total force on the loop is 0. Why? Because here, example of the rectangular current loop. Now, if the direction of the current is rotating in this loop. Now, the force on this side is equal in magnitude but opposite in direction by the force in this side. So mean to say that these two forces will cancel out. The same story with this, the force with this, the upper side will be cancelled out since they have the same magnitude and opposite direction with the lower side. So the net force on the current loop in a uniform magnetic field is 0. However, the net torque is not generally equal to 0. So if we have, so to show this, if we have a rectangular, this is the plane, okay, this is our plane. If we have a rectangular loop, okay, this is our rectangular loop, and this is the direction of our x-axis, z-axis, and the y-axis, z, x, and y. So if we have this rectangular loop in a plane, the magnetic field in this, for this sample, is directed towards the z-axis. So we have the magnetic field here, magnetic field there. So this rectangular loop has a side of, this side is A, B, this side is A. So a line perpendicular to the plane of the loop. So since this is the plane of the loop, it makes an angle phi with the direction of the magnetic field. Here. So it makes an angle phi with the direction of the magnetic field. This is the line perpendicular to the loop. So we define this line as the magnetic moment or the magnitude of I or A. So we'll discuss that later. The wires leading the current into and out of the loop and the source of EMF are omitted to keep this diagram simple. So the direction of our current is in that direction. Force F on the right side of this, of the length A, is in the x direction. So here. So the F and the negative, the force is negative F. The force here at this side is, this side is, we denote this F prime, and this is negative F prime. So, on this side, so the magnitude of force on this side is equal to IAB. Now, the force negative F prime with the same magnitude but opposite direction acts on the opposite side of the loop as shown in this figure. Now, the side with length B makes an angle of 90 degrees minus phi. So, their magnitude is given by F prime is equal to IB B sine 90 degrees minus phi, or this is equal to IB B cosine phi. So the lines of actions of both forces lie along the y-axis. Now, the total force in the loop is 0 because the forces on the opposite sides cancels out in pairs. Now, the two forces F prime and negative F prime in this figure lie along with the same line and so give rise to zero net torque. And each gives rise, the two forces F and negative F lie along different lines and each give rise a torque about the y-axis. So determining the torque is that from force to the lever arm, so the y-axis there, the y-axis. So both in the y direction. Hence the net vector torque is in the y direction as well. So the moment arm for each of these forces, the moment form is in these forces is equal to, the arm is equal to B over 2 sine phi. So the net torque in these forces is 2F times R, which is B over 2 sine phi, which is equal to F here is this. So natay B, 2 was cancelled, so sine phi. So we also have B. So A times B is equal to the area of this rectangle. So we have the torque is equal to IA B sine phi. So that is the net torque of this example. So this is the magnitude of the torque in a current loop. Now the product IA is called the magnetic dipole moment or the magnetic moment of the loop, for which we use the symbol mu. It is analogous to the electric dipole moment introduced. In terms of mu, the magnitude of the torque on a current loop is given by this equation. Our torque is equal to the mu cross B. So therefore, the net torque is maximum when phi is equal to 90 degrees. Then the torque is 0 when phi is equal to 0 or 180 degrees. Potential energy for magnetic dipole. When magnetic dipole changes orientation in a magnetic field, the field does work in it in an infinitesimal angular displacement. And the work dW is given by tau d theta. So, and there is a corresponding change in potential energy. The potential energy is least when mu and B are parallel and greatest when they are anti-parallel. So to find the expression for the potential energy U as function of orientation, we can make use of the beautiful symmetry between the electric and magnetic dipole interactions. So the torque in an electric dipole field is T is equal to P cross E. We found that the corresponding potential energy mu in the electric dipole is equal to P negative P dot E. Now, this is for electric. Now, in magnetic dipole, in a magnetic field is tau is equal to mu cross B. So, we can conclude immediately that the corresponding potential energy is mu negative mu dot B. So, this is the potential energy for magnetic dipole. In solenoid, A helical winding of the wire, such as the coil, wound a circular cylinder. If the windings are closely spaced, the solenoid can be approximated by a number of circular loops lying in planes at right angles to its long axis. Now, the total torque in the solenoid in a magnetic field is simply the sum of the torques on the individual turns. For a solenoid with n turns, in a uniform field, the magnetic moment mu is equal to Nia, and the torque is equal to Nia B sine phi. We have a solenoid here, and the direction of our current is there. Now, if we put the solenoid in a uniform magnetic field, a phi is an angle between the axis of the solenoid and the direction of the field. So this is the axis of the solenoid, which is mu. Then the phi is the angle between the magnetic field and mu. So the magnetic moment vector u is along the solenoid axis. The torque is greatest when the solenoid axis is perpendicular to the magnetic field and 0 when they are parallel. So the effect of this torque is tend to rotate the solenoid into the position where its axis is parallel to the field. Solenoids are also useful for sources of magnetic field. For example, a circular coil of 0.05 meter in radius with 30 turns of wire lies in a horizontal plane. It carries a counterclockwise, as viewed from the above, current of 5 ampere. The coil is in uniform 1.2 Tesla magnetic field directed toward the right. Find the magnitudes of the magnetic moment and the torque on the coil. So here, as illustrations for our problem, so we have a coil, and our magnetic field is directed to the right. There. This is the magnetic field with 1.2 Tesla. And the radius of this coil is equal to 0.05 meter. So, then the current is counterclockwise as viewed at the above, which has the magnitude of 5 ampere. So the magnetic moment is perpendicular to your plane. So we have, this is your magnetic moment. So magnetic moment is equal to Nia, which your area is equal to pi times r squared. So we have N, we have 30 turns, times I with 5 ampere, times pi r squared, which is 0.05 meter squared. So in turn, we have 1.18 ampere dot meter squared as the magnitude of the moment of a magnetic moment. So our torque, since our U is perpendicular to our surface, and it is 90 degrees from the magnetic field, so our phi is equal to 90 degrees. So therefore, our torque is equal to U cross B. So the mu, our magnetic moment is 1.18 ampere. So for example, if our B is at the x-axis and this is the y-axis, so we have at the J hat, ampere dot meter squared, sorry, J hat cross our B is 1.2 Tesla, this directed at I hat, So we have, so the torque is equal to, and sine 90 degrees. So our torque is equal to 1.41 Newton and is directed to the negative K hat. So that is our torque. Now, what is the Now, in our example above, so we need to find the change in potential energy, which is equal to U2 minus U1. So here, our U2 is equal to the negative, so the change in mu is equal to the negative mu B cosine phi 2 minus negative mu B cosine phi 1. So here, we could actually, to make mu parallel to B, so our phi 2, so this is our phi 1, our phi 1 is equal to 90 degrees. Then our phi 2, to make it parallel with, mu is parallel with B, so mu, our angle is 0 degrees. So we have negative mu B cosine phi 2 minus mu, cosine phi 2 minus cosine phi 1. So we have negative 1.18 ampere, that meter squared, times our B is equal to 1.2 Tesla times cosine of 0 degrees minus cosine of 90 degrees. So cosine of 90 degrees is equal to 0. So therefore, and cosine of 0 degrees is equal to 1. So our change in mu, or change in potential energy, is equal to negative 1.41 joule. So that is our change in potential energy.